in this lesson, I'm going to be talking about acid-base titrations, and what you'll actually realize is though I'm adding a new concept, this concept of a titration, it's actually material that we've already covered when we worked with acid and base dissociations and the common ion effect. So just a quick couple of definitions. A titration is the process of reacting a solution of unknown concentration with one of known concentration. And so you'll get a little bit of practice with that in the problems for the worksheet in this lesson, but then also with a full-blown lab in which you determine the concentration of a base given the concentration of an acid or vice versa. The next concept is the equivalence point. Now, the equivalence point is the point at which there are equal amounts of acid and base. And specifically, when we say equal amounts of acid or base, we're saying that you have equal numbers of moles of your acid and your base. So in a titration problem, what we're being told is that we have equal numbers of moles of your base and your acid. So the first thing we need to do here is actually write out the reaction between sodium hydroxide and sulfuric acid. So we've got sodium hydroxide reacting with sulfuric acid, and that's going to produce a salt, so sodium and sulfate, so Na2SO4, and water. Now to balance, I need to put a 2 in front of sodium hydroxide and then a 2 in front of water. And now what I can do, I'm trying to figure out what volume of sodium hydroxide is needed so that there are equal numbers of moles of sodium hydroxide and sulfuric acid. So what I know right now is that I have 0.150 molar of sulfuric acid and I have 200 milliliters of that. So what I want to do first is figure out how many moles of sulfuric acid that is. Because once I know how many moles I have of sulfuric acid, I can figure out how many moles of sodium hydroxide I need, and from that, figure out the volume. And so what I'm going to do is I'm going to start out with the concentration of sulfuric acid, and it's going to be 0.150 moles per liter, and that's just to help us with the stoichiometry. Then I'm going to multiply that by the volume of sulfuric acid that I have, which is 200 milliliters. So I'm going to convert that into liters. So I'm going to multiply by 0.200 liters. Okay? Now I'm in moles of sulfuric acid, and I can get into moles of sodium hydroxide. So I'm going to put moles of sulfuric acid on bottom. So there's 1 mole of sulfuric acid for every 2 moles of sodium hydroxide, and I got that from my balanced reaction. Now I'm in moles of sodium hydroxide. And I could finish the problem with this, but I haven't answered the question yet. So I know how many moles of sodium hydroxide are needed to have equal numbers of moles of sodium hydroxide and sulfuric acid. But the last step I need to do is to figure out the volume. Well, I know the concentration of sodium hydroxide. It's 0.150 molar. Well, since molar are moles per liter, what I can do is I can take the 0.150 moles per liter and put that on bottom, so moles on bottom, and liters up top. And so it's just a quick manipulation of stoichiometry to figure out how to get equal numbers of moles of base and acid. So here I've got 0.400 liters. Now keep in mind, just because my other volume was in milliliters, I'm going to convert this into mils. So I have 400 milliliters, and that's your answer. So while it seems like a completely different question, when you're doing a titration and when you're at your equivalence point, meaning equal numbers of moles of base and acid again, all you need to do is some basic stoichiometry. The last 2 terms that I need to talk about really quickly, and then I'll go further into investigating them, is first the end point. So while the equivalence point is when your number of moles of acid equal your number of moles of base, your end point is the point at which titration is complete, and there's not going to be any other color change. So if you've reached your end point, what that means is that you've actually passed your equivalence point, because as we'll see when we're talking about indicators, when you're at your equivalence point, you won't actually see a color change. It's right after your equivalence point, which is where your end point comes to play. Okay, so that's your end point. The last term, which we're going to be investigating in detail in this lesson, is your titration curve. Now, a titration curve is simply a graph of the pH, so the pH goes on your y-axis as a function of the volume of your titrant. So your titrant is what you are adding to either your acid or your base. So for example, in this example problem up above, in all likelihood, the 0.150 molar NaOH, that was your titrant. And you would have added that in a lab to the sulfuric acid. And we'll get lots of practice with titrations, but first let's look at some of the graphs. So here I show a titration of a strong acid with a strong base. So for example, hydrochloric acid and sodium hydroxide would be a great example. So at the very beginning, right at my x-intercept, I have 0 mils of NaOH, and so as you notice, my pH is very low because what I have at that moment is just all hydrochloric acid, so my pH should be low. As I move along to the right on the x-axis, I'm adding NaOH. So as expected, the concentration of my pH of my hydrochloric acid is going to decrease, which means my pH is going to increase. So I have more and more NaOH, which means I have less and less HCl. And then I hit this point at which the pH suddenly jumps up extremely quickly. And the reason why that happens is right before that happens, I've officially run out of hydrochloric acid to react with NaOH. And so what I have is actually just NaOH, is the OH minus in water. Okay, because as you notice, when your pH equals 7 right there, you don't have any acid or any base. They've completely reacted. And so once I go past that equivalence point where they're equal, and by the way, notice how significantly it jumped up to reach your equivalence point. Once I've passed that point, I only have base left over. And so I'm just having OH in that solution. So the pH is going to continue to spike up until it kind of plateaus up at the top once you get to around 70 to 80 milliliters of NaOH. So this is a titration curve for a strong acid and with a strong base. All right, and what we're going to look at now are practice problems in which we can actually use these in order to determine what exactly is the pH before I have equal amounts of hydroxide and hydrogen ions, what's the pH after that point, and then also what's the pH right when I have equal amounts. And notice at the equivalence point for a strong acid and strong base titration, it's actually 7. The pH is 7, meaning it's perfectly neutral. And you guys should actually understand that because the salt that's present after adding after adding HCl and NaOH, you have just water, which is neutral, and then NaCl. And that salt is neutral because they came from strong acids and strong bases. Now what we're going to work on, now that we've talked about strong acid and strong base titrations, we're going to work with strong acid being added to a weak base or a strong base being added to a weak acid. And so what this titration curve right here shows you is actually a strong base, an NaOH, being added to a weak acid. Okay? And so what you should be able to see if you start off right at the beginning of this titration curve, notice it's not quite as flat as the strong acid, strong base titration. Okay? You start off with your weak acid and you're adding your strong base. So yeah, the pH is going to increase quite a bit more drastically than when in the previous problem you were dealing with a strong acid and a strong base. Okay? Notice you're going to have that sudden peak up to your equivalence point, that increase in pH, and then past your equivalence point is going to kind of level off again. So it looks similar, but let's focus on how this is different than a strong acid, strong base titration. Notice that as you're adding OH, if you look at the drawings here, as you're adding OH minus, that actually converts your acetic acid into acetate ions, which we've already learned about at this point. Also look at your equivalence point, which is where your number of moles of acid equal your number of moles of base. Notice your pH is not 8. And if we think about that, when you have equal amounts of acid and base, if you have a weak acid, keep in mind that you're going to have a salt that's left over, and in this case it's your sodium acetate. Remember that that acetate ion is actually acting as a weak base, which is why your pH is a little bit above 8, which makes sense. So instead of having like NaCl, which is perfectly neutral as a salt, instead you're going to have sodium acetate, which is slightly basic. So when you're dealing with a weak base, strong acid, or strong acid, weak base, when you're at your equivalence point, your pH is not going to be equal to 7. Then notice once you've passed your equivalence point, the pH is going to be increasing because you're adding OH to a solution that no longer has an acid in it. What I wanted you to notice, we just talked about weak acids and strong base titration curves, and then also strong acid, strong base titration curves. I wanted you to notice, just really focus on how they look different. So on the bottom you have a strong acid, and so that shows the typical titration curve for a strong acid and a strong base. At the very top, notice the Ka is very small, so you have a very weak acid with a strong base. So let's talk about a couple of differences that you see based on the strength of acid that is reacting with the strong base. The first thing is that the weak acid is going to have a higher initial pH than the strong acid, which makes sense because remember, a strong acid has a very low pH while a weak acid has a higher pH simply because it has fewer hydrogen ions that have dissociated because it's not good at breaking apart. That's what makes it a weak acid. Another thing is that the pH change that you see to reach the equivalence point and beyond, it's less severe the weaker the acid is going to be. And finally, at your equivalence point, if you're dealing with a weak acid, then the pH is going to be greater than 7. And notice the weaker the acid, the higher the pH is at the equivalence point. When we're working with titrations in the lab, unfortunately, we don't get to see these nice titration curves. Instead, what we have to do is we have to use an indicator. Now, if you notice in this figure, this is showing you, for example, the one on the left-hand side is showing you phenolphthalein. So for phenolphthalein, it's going to turn colors when the pH is between 8.3 and 10. And so what this means, if you notice, for this titration curve in the top left corner, what that's showing you is you adding a base to an acid. And so you're going to start off with a low pH and then it's going to increase in the typical titration curve fashion. Now notice that in this case, phenolphthalein is a great indicator because the equivalence point is going to fall within that range in which the phenolphthalein is going to turn colors. And so that's a great indicator because as soon as it turns colors, you know you've hit your equivalence point. Because otherwise, there's no way for you to know when your number of moles of acid and base are equal. Since that is a good indicator, let's see what a bad indicator looks like. Methyl red indicator, it turns colors between 4.2 and 6.0 for pH. So if you notice here, if you have an acid and you're adding a base to it, that color change is going to occur way before your equivalence point is reached. And so that's going to be a bad indicator because, well, once it turns color, it's not going to turn anything else. So there's no way for you to know exactly when the equivalence point happens. Phenolphthalein in reverse, if I start off with a base and I'm adding an acid to it, phenolphthalein is going to be a terrible indicator because as you notice, the equivalence point is around 5, and that's not within the range at which phenolphthalein is going to turn color. So phenolphthalein is going to turn purple before you even reach your equivalence point, which is the whole point of doing a titration in a lab, figuring out where that equivalence point is. In contrast, methyl red would be a great indicator for this one because it turns that yellow color between 4.2 and 6 for pH. So you can add your acid to your base, and then once you've hit your equivalence point, you'll actually see that color change. Now, to reference back to terms that we talked about in the beginning of this lecture, the equivalence point is not when it turns that yellow or that purple. Instead, that's the end point. So in fact, you rarely will stop right at your equivalence point. Instead, you normally pass by the equivalence point or you're not quite there. So the end point is when it turns colors. So the last type of titration that we're going to be talking about is the titration of polyprotic acids. Now notice there are 2 equivalence points here, and the reason why there are 2 equivalence points is because you actually have 2 separate acids that are going to be reacting with the hydroxide ion. The first one is H3PO3, which is going to be losing one of its protons to become H2PO3, and once the number of moles of the H3PO3 equals the number of moles of OH, you'll hit one equivalence point, and then you'll hit a second equivalence point once the number of moles of H2PO3 equal the number of moles of OH.